But what I'm going to do today is like, because I'm going to talk about it, okay, here. And the group 4, who are group 4s for presentation?
Here.
Yes.
Okay, so I'm going to basically stop at this point after talking about this and this. A little bit I'm going to spoil basically the other group's presentation, but then I stop, they talk about the short lookup service, and then if there is anything missing, then I try to cover, okay?
Okay.
Okay, I'm recording. Okay, so today we're going to talk about peer-to-peer system and distributed hash tables. And basically the whole idea is to give you a little bit background about, if we're going to talking about core, the lookup service, I'm going to give you a little bit background about peer-to-peer system and hash tables and what are distributed tables. So let's start talking from the peer-to-peer systems. I bet most probably from the first day that I start talking about distributed system, or when you took the course distributed system, or when you mention it, the first thing that might comes to your mind is a peer-to-peer system. Seeing it as like a distributed system. I mean, one of the main things that might comes to someone's mind is peer-to-peer system, because something that we use most probably in our daily life. I mean, not just distributed system, but peer-to-peer system, I mean. So peer-to-peer system is kind of distributed system architecture that there is no centralized control, of course, and peers are communicating with each other. So, and nodes are roughly symmetric in functions. So there is no stronger server. All the basically nodes that are participating in the network, we can consider them having roughly symmetric function. Okay, let's say they're all PC, laptops, computer. Okay, there's no like a central control or central server that controls the network. So that's why basically the workload is partitioned, or the task partitioned among all these distributed nodes that are participating in a peer-to-peer system. So we can see it as a basically large number of unreliable nodes, because imagine all our computers, desktops or laptops or tablets are forming a peer-to-peer systems. Of course, they are not, they are just normal systems, they're normal computers, and they are not that reliable. So we have a large number of, basically a network of large number of relatively unreliable nodes. But considering the big number that we have, okay, we can use all these resources for processing power, for disk storage, and for so many other things, or network bandwidth even, we can use to utilize the peer-to-peer systems. So what are the advantages of peer-to-peer system? What can you think of it? Anyone?
So there is faster connection usually, right? In peer-to-peer. When the connection is established, there is later overhead on communication.
Okay. What else?
Many storage resources, I guess.
Mm-hmm. Right, true. What else we can think?
Usually it's easier, it's less easier to hack, usually. That's like security wise. But I don't remember, like this is old, so.
Okay. Okay. Yeah, you're right, actually. I mean, we can have high capacity for services through parallelism, because we have a lot of nodes, no matter they are still unreliable or they are not that powerful still, because there are so many. So we have, using the power of parallelism, we can achieve a lot of things. We have many disks, okay. For storage, we can use, we have many network connections. There is no, let's say, central server that makes it like a single point of failure. basically a big network connecting all together, and they have a big, basically processing power if we can utilize all of them. And as I mentioned, you have no centralized server. So as Paul said, less chances of service overload as load increase, right? A single failure won't wreck the whole system because there is no single point of failure. There is no centralized server that if the server fails, the whole network fails. And system as a whole is harder to attack, as Paul mentioned, right? So talking about adaptation, what services you can think of when we're talking about peer-to-peer, peer-to-peer networks, the system?
Torrent.
Torrent.
Torrent, file sharing, what else?
Gaming.
Streaming?
Yeah, and gaming.
Gaming, okay, yeah, of course.
Voice calls, video calls.
There are services, yeah. Even if I'm not mistaken, Skype we're using at some point peer-to-peer systems, right?
Blockchain, maybe.
Which one?
Gaming?
Blockchain? Yeah, of course. Blockchain, gaming. Yeah, I was seeing like a documentary about Cuba. That the whole, I mean, I don't know how accurate was that, but the whole gaming industry there was based on peer-to-peer systems, and like just normal people like providing like connection for their neighborhood, and it was pretty amazing what they did. I mean, by all those sanctions, and still they could come up with some sort of network, internal network, to be able to play games. Yes, all those are correct. So
Also,
go ahead.
yes, that's file sharing. I was going to say.
Yeah, they mentioned like file sharing. So we have client-to-client, legal, illegal file sharing. So we have popular data, but owning organization has no money. I mean, like all those pirate movies, softwares, and so on that you are aware of. As you mentioned, digital currency, there is no natural single owner like Bitcoin or any other cryptocurrencies, most of them. I mean, there are millions of cryptocurrencies now, so I cannot say all of them, most of them most probably. And how to say, anonymity network, right? If I don't know how many of you are using Tor, if you have ever used or you're using in your daily browsing. So Tor is also based on P2P network. So let's talk about classic example, BitTorrent, that is most familiar for us or maybe most used. And I've been talking about BitTorrent is not necessarily illegal activities. Okay, don't misunderstand it. Can be, you can look for basically legal sources too. Okay. So how it works, the BitTorrent, okay. So user clicks on the download thing, you download the torrent file, right? And which has the content hash, IP address of the trackers. User BitTorrent client talks to tracker in order to get the list of the peers who have the files, right? You download the torrent file, okay, or your muTorrent, you use the magnet, you get the file trackers, basically the client, if you're using like muTorrent, for example, that talks to the trackers in order to see what type of IP addresses having the content of the file that you're looking for. Then users, BitTorrent client downloads file from one or more peers from all those IP addresses, from one or from more than one of those IP addresses. Then user BitTorrent client tells tracker now it has a copy of files, okay, or some part of it too. So basically the ID will be informed to the tracker. Now tracker has this basically client IP address as well. So user BitTorrent client serves the file to other for a while, right? Is it clear? I mean, have you, who haven't used BitTorrent ever in the class? Wow. Press. So everyone use it, right? So you know how it works. So you get the files. Basically, that files later have the hash value of the contents. By that, you get basically you ask the tracker that what IP addresses have this contents. Then you connect to those IP addresses and you start downloading files. Then you have the files, a piece of files. Then you will be part of the whole network, and other people start downloading from you. This is not the only way. Okay, this is the classic BitTorrent when we're using trackers. There are examples that we don't use tracker, and we're going to talk about it. So using this, it provides huge download bandwidth without expensive servers or network links. I mean, if you haven't used it, you know how fast it can get and how reliable it is. I mean, the whole network. I mean, reliability on not just particular nodes, one nodes, but the whole networks. Usually there are like basically, I mean, people that you can always download the files, especially when it's popular files. So, but there is a problem there. Okay, so imagine this is like a peer-to-peer network of BitTorrent. We have the internet, we have all these nodes that are connecting. Okay, so let's say I'm the client, I'm using for Star Wars movies, I want to download and I want to watch it again once more. And there is a publisher, like let's say Node 4, that has this file. Okay, so the problem is now how we can find, how the client can know, okay, or me, I can know this publisher has the content. So the whole idea for today's class is about talking about lookup problems, okay? The short is about lookup services. So how many of you remember Napsters?
Me, all of us, I guess.
I assume most or all of you. I mean, so Napster was using like a centralized lookup, or basically there was a like centralized database that the publisher would say, okay, I have a copy of this, let's say movie, or like let's imagine that that's a soundtrack, okay, because Napster is more popular for music. You have this soundtrack, the client is looking for it, so your client can directly connect to the database and basically get the can ask database, and database can say, okay, this publisher and for IP address has the file, so then I can connect to the publisher and start downloading it. But it's not a good trade-off for peer-to-peer systems, okay? Because okay, that's what I was saying. Because though it's very simple architecture, but basically the complexity is linear, as you can see. As I put here, the complexity is linear and it's not that efficient. And there is a single point of failure. Another problem with this, though it's simple, complexity is high, and also there is a single point of failure. If the database is down, I mean, the whole network is down. I mean, there can't be any file transfer there. So we should look for a better idea. So GNetella, I don't know if you heard about it or not. This is basically was first decentralized peer-to-peer network that uses basically these flood queries, and it was the first one. Okay, so a lot of other systems developed on top of this or based on this. So what it was doing is was using basically flooded queries. So you can see in this example, how to say that the complexity is lower. Okay, it's still not great. It's a robust systems, okay, because there is less query in the systems, but the complexity is high, and sometimes in order for client to find out basically the content, which system or which node has the content, the message need to flood in the network, okay, and that's flooding consume a lot of resources. So there should be a better way, not just this, a better way. So we want basically, we're going to talk about this, okay, rooted distributed hash table queries or curve. So we want basically to find the content holder with a very few queries, okay? With a very few, let's say, RPC packets, not cloning the whole network, not accessing the centralized database. So we are looking at a better solution, okay, to be robust, reasonable state, and it's also reasonable number of hops. I don't want to ask this, ask this, ask this, ask this, ask this, and find this. I want to jump to the publisher with a reasonable number of hops. So what we can do in order to achieve that, we can achieve that using distributed hash tables or hash tables. I'm going to a little bit talk about this too, okay? So what is the hash tables? Anyone? I mean,
So yeah, that's like a structure where you have like a key with several values usually, and when you process and when you want to look for a value, you process it somehow in a constant time, so you get a key, and that key points you to the right direction of where the values are located.
Sure.
So that
how do you generate the key?
With a hash function, it's called usually, right?
Yeah,
so you process the data somehow, like for example, you can sum all the digits from a number, let's say, and that's your hash. That's an example, and that will give you a result, right?
Right.
And so for several values, you can have exactly the same keys, but all the keys are stored together, and then you can hash it with a secondary hash function or something like that, right? But it decreases a lot the lookup depending on the amount of slots that you have.
Exactly. I mean, yeah, Paul said it perfectly, and he said even about basically having duplicated hash value. He covered even slightly more. I'm not going to talk about that, but that's exactly correct. Basically, hash tables is a data structure that uses hash function to compute the index of the file. You can look at it this way. You have the basically a file. You can calculate the hash and then put the value in the hash function basically in that index that you're generating using the hash value. So next time when you're looking for it, okay, so you generate the hash value for what you're looking for, then you directly go to that index and your content is there, or the value that you're looking for is there. Sometimes they use this example of, let's say, like a phone book, okay? So for example, in your phone, you save all the names, all the numbers by the names, right? So when you want to look up for a number, you're not going to go through all the numbers, right, to find the numbers. You search the name, you find the numbers. So that can be an example. You can think of it like that. So how fast you can directly go to the name and find the numbers, right? You're not going to screen everything. So the hash tables also work the same way. Which you have the value you want to store, right? Then you can basically get the hash of that value or the name of the value, okay? So it gives you a number, right? Then you go to that index in your table, you store the value in that index that you generated here. So the next time you're looking for that, you can directly make the hash, get the index, and go directly to that index. So you see how fast it would be the lookup services. So it's the constant time insertion and lookup when we're using the hash tables. This is the hash tables, but we want to talk about the distributed hash table. So distributed hash table is doing almost same process, okay, but across millions of hosts on the internet, not just in one part. We want to do the same process across different hosts. So using the same analogy of the phone book in one phone, you can think of it. For example, we are having we are having all the people in this class in our phone book. Okay. imagine this class is like 10,000 students, then you have all these 10,000 numbers. Okay, then there would be one person join, then 10,000 people need to update. If you want to have this one copy of all the numbers, and 10,000 people need to update that phone. But using distributed hash table, we don't need to restore all that. We can distribute that basically phone book among all these 10,000 phones. Okay, so each phone can have part of it, but for lookup, then we can use, for example, I get the hash value of, let's say, Jose Roberto names. Okay, give me a number, then I know that number is stored in a certain phone. I go to that phone directly and I get the number. So it's just analogy, maybe it doesn't make much sense, but I thought it can maybe simplify it a little bit. So any question about hash tables? Because if you don't get this, you don't get the rest of the class, basically. Okay, so we want to talk about distributed hash tables, and I already talked about this. What's distributed hash tables? So it's basically, again, a decentralized storage systems that provide us with a lookup and a storage, okay, across multiple nodes, okay, using the hash tables. So basically, you generate the hash value of the data that you want to keep. Okay, it gives you the key. Okay, in that lookup key is basically associated with the IP address of the nodes that have that data. Okay, so then you can basically have this RPC, okay, like IP address put in this key and this data, okay, and basically the key is generated from the hash value of the data. And for getting it, again, the same thing. When you put the IP address get and the key, then you get directly the data. So it partitions data in a large scale distributed systems. Okay, so you can look at it as like tuples in a global database engine, data blocks in global file system, or files in P2P file sharing system. So we can use basically distributed hash table for all these purposes. Okay, not just for files in P2P file sharing, but for data blocks in global file system, or even the tuples in a let's say global database engine. So the whole idea of basically the distributed hash table is, as Paul also said, is like generating hash value of the data in order to get the key. Okay, then always if I want to look for this, I can generate the hash value, get the key, and that key basically directly lead me to the IP address of where it is stored. So we can have cooperative storage with the distributed hash tables. Okay, imagine you have distributed applications. You have distributed hash tables that you have this basic function. You can put data on it. You can get the key. I mean, if you put the basically get with the key that you have it already, okay, generating from the hash, you can get the data. Then we have this lookup service that we're going to talk about this. Okay, how we're looking for it, because imagine we're talking about like millions of nodes, okay? Data is distributed so much, okay, then the lookup isn't that, it's not basically a trivial problem, finding where your information is stored. In that 6, you say, okay, ask this, ask that, ask this, ask this. After 5 times asking, you can find where the information is. But thinking about a real distributed system that like I don't know, like in P2P network that there are like tens of millions of computers connected together, then it's a really challenging task, okay? So apps may be distributed over many nodes, as I mentioned, and distributed hash table distribute data storage over many nodes too. So that many nodes can be up to tens of millions of nodes, okay? Not just 5, 6, 10, 20, 100. Can be tens of millions of nodes. So let's talk about the same example that we did last time. We talk about classic BitTorrent using the tracker, how we basically utilize that trackers in order to find the IP address. But we can have BitTorrent over distributed hash table, which is, if I'm not mistaken, is applied in most of the current BitTorrent client, uTorrent. If you're using that, I'm pretty sure using BitTorrent. I mean, they have these options. So BitTorrent can use distributed hash tables instead of trackers or with the trackers. So in this case, we don't need the tracker. We don't need a tracker to get the IP address from. So if we don't have trackers, what we can do if it uses distributed hash tables for generating the key, again, the same things as I mentioned, file content, we make the hash of the file content, okay? And we call it or info hash of the contents, and that gives us the key. And the value, sorry, the value will be the IP address of the peers willing to serve the files, okay? So we have the key and we have the value now. And what the client does, okay, clients can use the, let's say, get functions. If you use the get function with the info hash that you have, you can find other clients, okay, that have the file or willing to serve. And in order for the put, you can basically identify yourself as a willing node to serve the file. So we have the basically generating the key from the content of the file, hash of the content of the file or info hash, and then the value would be basically IP address of the peers that want to serve the files. So what is the benefits of using distributed hash tables but not a tracker? Because the trackers can, like, imagine now we have a central single point of failure. If it goes down for illegal attacks, like what happened to Pirate Bay, for example, due to DOS attacks or DDoS attacks, it can go down the server, so the system will be basically affected. And also, distributed hash tables can work like a giant tracker, single giant tracker that is distributed over many nodes. And it's a less fragmented than one single trackers. So because of that, peers have more chance to find each other and in a faster and easier way, easier fashion. So that's why it has, I mean, using even BitTorrent with distributed hash table is much more efficient than using BitTorrent with single trackers. So as I mentioned, it's not really like that easy, okay, designing distributed hash tables, okay. It is decentralized, okay, and it's we don't have any central authority. All the basically nodes in the network, they are peers to each other. There's no, as we mentioned, there's no single server there controlling everything. And how to make it scalable, okay, to make sure that we don't have low network traffic overhead. These are basically actually the advantages of the, let's say, peer-to-peer systems, right? It's a decentralized, it's scalable, it's robust, it's efficient, but achieving that isn't that easy using, I mean, distributed hash tables. And also it should work efficient because we want to find the items quickly. If I'm looking for a certain keys or a certain content, I need to find that with a very low latency. I'm not gonna wait like minutes or few seconds for me to look for the information. Few seconds, maybe in some cases, fine. And it should be robust because node fails. I mean, we are talking about millions of unreliable nodes in the network. So they fail, they get in the network, they get out of the network, they connect, they disconnect. So the churn or this rotation of the nodes, joining, leaving, failing, it's high. It's very high. In some cases, like 100%. There we have 100% churn in the network. Okay. So I'm going to stop here. Okay. So the rest would be talking about short or court lookup service. Let's see how they're going to pronounce it. We would listen to them, okay, but later I will again go through my slide a little bit faster, okay. If there was like missing content, I will talk about them, but please try to catch the idea when they are presenting the idea. And yeah, we'll continue like that. Let me stop sharing.
Protocol, and Ricardo will help me with the introduction.
Yes, as Saul mentioned, we're going to talk about CORD. Can you go to the next slide, please? First, we'll go to the outline of the presentation. Well, as Maria already mentioned, we're going to talk about peer-to-peer applications, general characteristics of the CORD protocol. We're going to specify a little bit more about the information that is held by the CORD protocol, like the finger table, how nodes are joining, how they're leaving. The fourth part, we're going to see some results, experimental and simulation results from the paper. And at the end will just be a summary of the characteristics of the CORD protocol. Okay, so as Mari mentioned already, what are peer-to-peer applications? So they are applications that don't have any centralized control. I'm gonna be a little bit faster on this place because I mean, Mari already mentioned those. So the features that peer-to-peer applications have are—
Don't worry about it, you just take it with your own pace, okay?
Okay.
Repetition is the key, so no worries.
Yeah, so some of the features for peer-to-peer applications are, for example, redundant storage. One server can have information from, I mean, several computers, clients can have several information from a single file, and that way, I mean, you can get information from different clients in this network. It also has the feature that is anonymity, that is not a centralized server that has all the information. You can have certain anonymity in this network. You can also have some features like a search of information, authentication, and among several others. Here we can see a picture of what are the differences in these two topologies of network. And the left you can see a server-based, where there's just a centralized computer where you go and get the information from. And on the right hand, you can see the peer-to-peer. In the case for the left-hand side, if you have lost the connection to the centralized server, there's no way you can get that information from any other computer or any other client. Which in the peer-to-peer situation, you can get information from different nodes in the same network. Even if one of the servers are failing, you can get that information from other computers. Here's another example of a topology of a peer-to-peer network. As you can see, in the node number 9, if you have an MP3 song that you are trying to find, if you as a member of the network had the information of all of the nodes in the network, you might be able you might have to go by computer to computer to find this information. In this case, for example, depending on the order of this, you can go from the server 1, then to the server 2, to the server 3. That way of finding that file that you're trying to download. And in this case, you have implemented 9 searches. But for example, in the case that the order that you have this server's connection is different, and you go the other way around the circle, you can find, I don't know, I think it's 7 searches until you find the correct server that has the information you find. That's why having information for all the nodes available in the peer-to-peer network is not a suitable situation. Apart from you also having to store all that information, you are not sure where to find that information. So you have to find a way in order to have this search mechanism more, you could say, fast. Someone call you. Again, you can go to the next slide. This is over. No, before. Yeah. Not the one before. Okay, yeah. The problems that short the algorithm, what are the problems to solve? Well, as mentioned by Mari, some of these characteristics are also solving in part by the peer-to-peer network topology. So you have a load balance. Since it is a distributed hash function, it is decentralized. It has high availability since one node joins or one node leaves. You can still have the information available for the rest of the nodes. You have flexible naming. That means as the key space for these nodes available in the chart is flat, you can also have some flexibility in the way you have the pair of the keys and the values. Can you go to the next one? So some of the general characteristics that you will also see in the summary on the last slide is that the chart, given a key given it maps the key onto a node being a computer on the network. So depending on the application, the node may be responsible for storing the value and the associated key. In this example, we're going to see that the node is indeed being responsible for storing the key and the value that you're trying to retrieve from this node. The short algorithm uses a variant of a consistent hashing to assign keys to the nodes available. And one of the important features that this mechanism has is that each short node, each computer in the network, only needs routing information of only a few other nodes, and it doesn't need information for all the nodes available in the network. So having a system of n number of nodes in the topology, each node maintains information of at most big O log of n, n being the number of nodes in the system. It resolves a lookup in no more than big O log squared of n. That means, for example, in the first situation that I mentioned about the MP3 being available in the server number 9, you will need to have information for all of the servers. That means n of the servers. And the lookup could take up to n number of servers, of search, sorry. In this case, the lookup for this information will take a significantly less amount of time. Another important thing is that when another node joins or leaves the network, only a fraction of the keys as the values or the files or the thing that you're storing in the servers, only a fraction of them are moved to the new server, and not all of them have to be rearranged. Okay, so here we can see, for example, this is the, Saul is going to explain a little bit more about this later, but this is the circle that is going to explain in how the topology is in the chart algorithm. So the keys are stored in these 3 nodes. The green ones are the active nodes. The node 1, node 4, and node, I think it's 8. Key 1, key 2, and key 5, and key 6. But where is the key 15 going to be allocated? As we're gonna see in the algorithm later, we're gonna see that yes, you can go. We're gonna see that the key 15 is gonna be assigned on the node 1, given the algorithm that Saul is gonna explain later.
Okay, so all the things that I have seen so far, we need to put it on the table to know what we are talking about, because now we have the benefits, but we need to see how CORD works. As Ricardo said, the CORD protocol, his main purpose is to storage keys. As we've seen in the examples of the professor, he put an example of a file, a movie file, a Star Wars file. We can storage that file in a node, and the key of that file could be the name of the movie. So in order to relate the key and the value, we storage that pair in a node. But the nodes are assigned to each node following the that rule. So we assign IDs to nodes that are greater or equal to our current key ID. So for example, the key 1 will be stored in the node 1. The key 2 is lower or equal to node 4, so it's storage to node 4, and so on. So in the case for the key 15, when there are no more nodes, we assign it to the next one node available in the layout. But in order to understand this schema, we need to introduce what its name, that it's an identifier circle. In the core protocol, the identifier circle is a topology of nodes that it's built with this formula, 2 raised to the m power, where m is the number of bits that we need to identify each node in the system. I'm going to open a parenthesis. When I talk about a node, I'm going to talk about a computer, our PC, our laptop, or a node in this core scheme. So I'm going to use that indistinctly. So when I say node, I'm talking about a computer or a space in the circle. Okay, so in an identifier circle, if I want to have, for example, 16 nodes, I'm going to need 4 bits, because 2 raised to the 4th, it's 16 nodes. And I'm going to tag each node with that identifier. So for example, this identifier circle have 16 nodes. I can storage up to 16 computers. And the first identifier will have the first value, and so on. So now that we have the topology of the core protocol, we need to assign the new computers. When a new node joins, we need to assign in an identifier. I have to know how a new computer will be assigned to one of these places. So this is where the hash functions comes in. So what we need to do is, when a new node wants to join, I need to hash their IP, their IP address. I obtain a string 160 bits long, and I need to truncate that string to the m bits that I am using. So at the end, I'm going to have a hash of 4 bits. That hash, I will just assign it to a node. So for example, when this IP is joining to core protocol, I have a hash, I have an ID, and I'm going to assign this IP to the node with ID 0, and so on. As soon as the new node joins, I hash the IP, and I obtain the an identifier, and I will assign it to a node. So when we have said that, with this information, we need to remain that in core protocol, we don't need to store the information about the all other nodes. We just need to know about a few nodes. And in order to achieve that, we need something that is called finger tables. Finger tables, it's a routing table that maintains just m informations. In this case, m, well, since m is the number of bits, in this case, I will have a finger table with four records for each node. So instead of each node have 15 references to other nodes, with core, we only need to maintain reference to 4, in this case, to 4 nodes. So how this finger table is constructed, how do we build this finger table? We need to use this formula, which is n plus 2 raised to I minus 1, and that operation module 2m. For this particular scenario, we have that m is equal to 3, because 2 to the 3, it's 8. And here we have 8 nodes. The n is the current node that for where I will calculate its finger table, and the I it's the finger or the row in the table. But if I have a constraint, it should be greater than 1 and lower than m. So if we evaluate this formula for the first node, we will have this. We replace the values. We are in the node 0 and plus 2, and my first finger is 1. It should be greater or equal to 1. It's 1 minus 1 module 2 to the m. If we evaluate this, we will have 1. This number means that the first finger of node 0 is 1. In other words, node 0 should know node 1. If we evaluate the second finger, we make the operations, we will have 2. That means node 0 should know node 2. If we evaluate the finger 3, we will have a 4. And that means that finger 0 should know for node 4. What I'm saying should, because not all the nodes are always available. In this case, only the green ones are available. So what happened with the node 2 and the node 4? In this case, they are not available. So what I have to do is assign it to the next node available. And they follow the same rules that the keys. The nodes are assigned to well, they should assign it to a successor will be, of course, greater or equal than its current ID. So for example, node ID exists, so his successor should be 1. Node 2 doesn't exist, but node 3 should exist, so it should point to node 3. Node 4 doesn't exist, but node 0 does exist. So I should point node 4 to node 0. So as we see, each node maintains a routine with at most m entries. In this case, this node just only need to know 3 more nodes. They don't need to know the 7 remaining nodes. So despite the node ID and the successor, we also need to know an interval. That's mean interval between fingers. So for example, we are still in node 1. To calculate the interval, we should know where the finger 1 starts. And my finger 1 is okay. My finger 1 starts in node ID 1, and my finger 2, which is the next one, starts in node ID 2. So my interval is from 1 to 2. For my finger 2, it should go from finger 2, that it is the current one, to, in this case, should be 3. This is a typo. It should go to the finger 3. So in this case, it should be finger 3, and this should go to 2, which is where the node 0 starts, to the 4, 3, and the node 3 starts in node 4. So this should go from 2 to 4. And the 3 finger should go from where it's here again, this is a typo. The node 0 should go from from where a finger tree starts, which is 4, to where I'm starting, where up to the node I'm working on, which is node 0. In this case, it's finger 0, and this is a typo. This should go from 4 to 0. So with these intervals, I can find another node. So this helps to reduce the time of looking in the table. So now that we have this routing, what happened when a new node joins to the network, or what happened when a new when a node leaves the network? In this case, I have my identifier circle. The blue ones are the active nodes. And what happened if in the protocol, the node 9 wants to join? When it joins, he needs to perform the first actions, that it's all their keys that are related to its successor should be reassigned to the new node. Why K8 and K9? Because they are lower or equal to the current node. So in this case, when the node 9 joins, he requests for this key, for their keys, and node 11 needs to date its predecessor to the current one, and node 7 needs to date its successor to node 9. And what happened when a node leaves? The same things happen. When it leaves, it should assign their keys to the next one available node. In this case, is node 7. And node 7 and node 3 also needs to reassign their tables in order to know that node 6 is no longer available. So in this case, when node 6 leaves, node 7 needs to date its predecessor to node 3, and node 3 needs to date its successor to node 7. And now with this, we can go to some results that are in the paper, and Ricardo will help me with that.
Yeah, just a quick, can you go back in the last slide? Yeah, I mean, when Saul mentioned about that, when this node 6, for example, in this case, leaves the network, the core protocol doesn't do it. I mean, the node itself doesn't do it. At the end of the day, core is a software that is built, there's like a layer in the software that has another application on top of it. This top layer application has to do this kind of operation. There is, for example, this top layer application knows how many nodes are available, how many nodes leave, and in general, how is the topology. So in the case, the higher level application knows when that, in this case, the node 6 leaves, is the higher level application that makes the request for your reassignment of these keys to another node. It's not like the nodes like, okay, I'm gonna go and I'm gonna send my information to other nodes. It's just like, has to be like a cooperation between the core protocol and the higher level software. Okay, now you can go to the results part. Here we can see the results for the path length. What is the path length? The path length is the number of nodes it traverses during a lookup operation, meaning you are in a node N, let's say, and you have to find a certain key. To find that key, you are going to have to ask X number of nodes for that information. And every time you go ask for a new node, or that node ask for another node for that information, it's like a jump in this path length. We can see here in this graph that the number of nodes, as the number of nodes increases, as well increases the path length. That means, for example, in the first case, this 8 number of nodes. This is in a simulated environment. So this is a network of 2 to the n 2 to the k nodes, where k starts from 3 to 14. And every, the keys to store are 100 times 2 to the k, to the key. So that means, for example, in the first case is 2 to the 3, that means there are 8 nodes. And the number of keys are 100 times 2 to the 3, that means 800 keys. So there are 800 keys to store into 8 nodes. That way you are increasing this, in these test cases, the number of nodes. As you can see, I think there are, at the last part is, I don't know if 8,000 or 4,000. I believe it's 8,000 nodes available for 100 times 2 to the 14 keys. So the number of keys increase by a much larger amount than the number of nodes. And we can see that the increase in the path length, that means the queries you have to do to other nodes, does not increase related to the number of keys. It increases as expected in the paper as big O log of n. This is in a simulated environment. Could you go to the next one? They also performed some experimental results. They performed they have like a network for this kind of test situations. They have different nodes in parts of the US, for example, New York, California, Colorado, Massachusetts, North Carolina, and this is where Philadelphia is, I don't remember. Pasadena, no, not Pasadena. Well, the other state. So this short protocols uses, well, it runs on Unix, and it uses 160-bit keys obtained from a cryptographic hash function. That means the keys are gonna be passed to this hash function. And these keys are gonna be 160-bit in size. And it uses TCP protocol to communicate between the nodes in these other locations. I don't know if you can see very well in the presentation, but the median latency, that means the time that it takes from one request to receive the key information, is from 180 to 285 milliseconds. So in the case, for example, of 180 nodes, a lookup involves 5 two-way messages exchanges. That means you have to go and ask a node, okay, do you have the key? No, and they have to respond to me. That is the two-way message exchange. So it involves 5 of these messages, and 4 of which are the short lookup, and the final one is the actual request for the key into the node that has that information. So the expected, and in the paper they have this expected value that it will take for this lookup to be is about 300 milliseconds, and we can see that a median latency is below that value. That is below, and between 180 and 285 milliseconds. So they can prove their theory by the experimental results. Okay, so this last part is just the summary of the raw data of this protocol. So basically what they're trying to do is that given a key, it maps that key and that information into a node available into the circle. It uses consistent hashing. That means because they want that information to be available in a way that you can have the same, roughly the same number of keys available in all the nodes. That means they're trying to minimize the way that, for example, one node has 60% of the keys and the other nodes doesn't have any keys, and so they are not requested for information. So they have this consistent hashing for the nodes available in the network to assign this information to each node. That's why it is important. It's part of consistent hashing. the core protocol only needs routing information of only a few nodes. They don't have to know the complete topology of the peer-to-peer network. And in this, we can see also these data where we can have, for example, in the net node system, they have information only of big O log of n nodes. And the lookup results in no more than log squared of n. This I have to remark this part, that as an average, the average of the lookup will be big O log of n. But in the case where the system is very dynamic, where there are nodes joining or when there are nodes leaving the network, this value is increased to big O at the most, big O log squared of n. I mean, that is, even though it could be a big number, it is still lower number than when you know the whole topology and you have big O of n of the network. So I don't know if anyone has any questions at this point.
Yes, I have one.
Okay.
How do you calculate the successors?
Yeah, could you go back previously in the presentation to?
Yeah, and the other. Yeah. Oh.
Okay. You want to answer?
Sorry?
No, I'm talking to Ricardo.
Okay.
Yeah, I was talking the next one. Oh, no, the previous one. Where is the table?
Okay.
The table for the.
Yeah, that one.
Okay. Yeah, when there is a node joining at the end, we have to take into consideration that this is not the higher level solver. So when a node joins, the higher level solver knows that. So there is a way that there are 3 steps for, I think you paused that coming before, Saul, the 3 steps when a node joins. I think it's a slide.
Yep, I found it.
Oh yeah, that one. So when a node n joins, there are 3 steps you have to perform. One is the initialize the predecessor and fingers of node n. Node n is the one that joins, and this is by help of the higher level software. You also have to update the fingers and the predecessor of existing nodes. How it does it is when a node n joins, there's like mentioned in the paper, like one optimization of this is to have the finger table of a closed node to be copied into the end node, and then the end node has to ask these other nodes to update of this information. That means when one node joins, it asks the other nodes in the network to tell them the successor and the predecessor, so they can all communicate between each other to know the exact topology of where they are located into the circle. So it's doing by the communication, the higher level software, and communication to the other nodes by asking them for the predecessor and their successor.
Well, actually, my question was a little bit different. In the finger tables, you say that you're calculating. Can you go to the table, please? Yeah, there. You are calculating in the previous one. Yeah, that one. You are calculating the node ID for the finger, and then you said that you need to have, like, for example, node 2 and node 4, they are not available, so you need to select a successor. So how do you know that, for example, for 4, that successor is 0 and not 3, for example? I mean, 3 is closer than 0, but
okay.
I don't know if you have a rule for calculating that.
Yeah, as Ricardo said, the core protocol doesn't make that calculations by itself. He needs a higher layer. That means your applications. Your application is aware of all the available nodes. What core protocols do is just to make processing and inform to the high layer. So your application now knows which nodes are available. So they communicate with the core protocol, and for example, these values are performed by the core protocol.
Yeah.
In that, if you made operations in each layout, you always have these values, but these will be different according to your applications. So core protocol notify your application, hey, I'm in charge of this node, but your application will say, hey, that node is not available. You need to assign it to the next one that it is available. So the short answer is your high-level layer knows about the available nodes.
Okay, got it. Thank you.
Welcome.
So just to, in a few words, what you said is that the successor and predecessor calculation is performed on application side, right?
Yeah, because when a new node joins, the core protocol just assigns an hash ID with a node ID. But for example, when a node is joining, in this case, how this node knows to which, for example, to which node needs to request IDs. The applications tell that node, hey, you need to add at this node for the keys, and need to take you need to take information from this node and from this node. And yeah, the application is the what that rules.
Okay.
I have a question.
Yeah.
For example, Ricardo, you mentioned that you have different nodes that are sharing information, but how can I ensure the security
Of the information. Okay. The security of the integrity of the information, or the security of the process?
About the information?
But what do you mean with security?
For example, different systems are sharing information. And what happens if, I don't know, I try to hack the system or the system over the communication between the different nodes?
Okay, that's a good question that I think Paul already answered. It's because their way in the core protocol is implemented. One of the main attributes is that you use anonymity. So and it's harder to hack. So if you want to try to hack the system, you mostly have to ask for a specific key that, as we say, the key is a hash of an IP. So the first thing is you need to figure out what that key ID is. So once you have that key ID, you can look up through the system, but it's like to a blind search, because you are trying to search whatever you want. You are not looking right for information, you are just looking for whatever. So the first thing that you need to do is find the key ID to enter to the application.
Yeah. To add to that, I think, for example, in this case, the number of nodes and the bits used for the key are only, in this case, 4 bits. But in the example they use a cryptographic hash function that creates a key that is 160 bits. That is, I think they mentioned in the paper that is, I don't recall the exact phrase they use, but it's almost like impossible to decrypt this information. So you cannot just guess this key value and just try to find this other node.
Okay, got it.
have another question.
Yep.
Uh, we need bits in order uh, to see how many nodes we are going to get, right? So
Yes.
the number of bits that we need, where those numbers come from?
Okay.
You already say it, but I just missed it.
Okay. It almost depends of your application. If you want to host 16 nodes, you need 4 bits. If you want to host 1,000 to 24 nodes, you need 10 bits. So it almost depends of your network.
Oh,
How many nodes do you want to host?
okay, so that is something that I do assign in the case
Yes.
if I'm constructing it. Okay,
Yes.
got it.
Yeah, because it
Yeah.
depends of your architecture. If you need a small network, you will use 1, 2, 3, 4 bits. It's up to you.
Got it. Thank you.
Yep.
Yeah, so I have a question related to the previous question. So you have to define previously how many nodes we're going to have. I mean, in the example that you have in the presentation, it's 16 nodes. But what happens if if you want to add another node, you will have to increase the exponent. So you will have a bigger hashed key. So you will have to update all of the keys, or you cannot increase the number of nodes.
Yeah. For example, in this case, we use this number of bits for this instructional purposes. But for example, in the paper, they use this this encryption hash function that creates a key into 160 bits. So that in that case is 2 to the m. That, I mean, if you design your system with a big enough number of bits available and values available for nodes, and you can in terms be sure that you will not find this kind of situation, you have to do these modifications. So it is also as a peer-to-peer protocol, it is thought to be scalable. So you have to have a space, in this case m, big enough to handle different, I mean, numbers of nodes joining or leaving the network. So I think maybe having this topology for just 4 bits and only having 16 nodes is not something real to be happen, something that's going to happen, but having the system be designed to have a large number of nodes, to have thousands or maybe millions of nodes available.
Okay, thanks. But like, who designs it? Because it's like peer-to-peer, so who has like the?
I mean, it depends on your application, and you're the person who's creating the application. You're gonna decide it. But yeah, I mean, the paper doesn't mention anything in this kind of situation. Just because they mentioned they use this 160-bit space.
Okay, thanks.
I think another answer could be it's depending on your applications. If you need more nodes, you just increase your M and you will able to host more nodes. The core protocol just allows to make the reference to other nodes. So we can say that core is reduced to this could be reduced to this formula, because this tells you what other node you need to storage independently of the number of nodes. So you can increase, you can modify your architecture it's not a constraint. Once you set an M, you can modify it.
Okay.
Any more questions?
I would like to add, if you allow us, Maddie, we talk about the finger table, but we don't know how to use the finger table. We don't know how to find data.
What?
So if you let me, I would like to explain that.
Sure.
Okay.
You don't?
I hope some of you were asking that question, but I have not looked. So as we can see, this table, it's the finger table for node 0. That is the same that the one that we have used with the typos. But the finger table storage, or the nodes that we should know, the real nodes that are available, and we also store more information that are the keys. That means the key of the data that we are storing. We also have the IP of the node, the port of the node, and some other things that help us to recognize that that node. So for example, what if we are in the node 3 and wants to find the key 1? What should you have to do to find this key? In a traditional way, we can make some jumps. We can do tasks, ask to each node in order to find this. But core protocol help us to improve the search. So in this case, what protocol do is look in its finger table if I have a node that it's greater or equal than my current key. So for example, if I'm looking for the key 1, I'm going to look in my finger table if I have a successor that it's equal to this one. So is lower or equal to that key. So I go to my finger 4 and I see that my successor is 0. In this case, all my my fingers point to the same node. So I move to the node 0 and I'm asking if he has a node which ID is if the key is greater or equal than the node ID. So I come to node 0, I look in my first finger and I see that I have a node ID with ID 1. So I move to the finger, I move to the node 1, and I ask this node, hey, do you have the key 1? He say yes, and this answer this. So with the finger table, I just made 3 steps in order to find my key, instead of make 1, 2, 3, 4, 5, and 6 steps. So this is how we use the finger tables. So any questions about this?
No questions? Actually, the last part that Saul just talked was the main part, actually. How do you do the lookup? Okay,
yes.
He just explained the lookup.
Yes, because the key inside of the core protocol is the lookup.
Mm-hmm.
You look up for a key in a short period of time.
No question? Okay, thank you. Thank you. Thank you, guys. Okay, I send you a link to the chat for everyone. So you can simplify it for you. So you can use just the link, you don't need to. Okay, so I'm going to share my screen. Basically, this is what you're doing. Okay, I'm going to go through my slides too, but faster. They covered everything. But, okay. Do you prefer to have a short break, or should we continue and finish earlier?
Let's finish earlier.
Yeah. I'm just hungry. I want to go. Okay. Let's see how fast I can go. So, okay, skip some. Okay. So anyway, for code, they always say they use SHA-1. Okay, SHA-1 is a basically hashing algorithm or cryptographic algorithms that you give the value and generate a 160-bit string, but not necessarily you're going to use 160-bit string, because you can truncate it to M bits, as they were talking about, the M bits that you want. Because if you consider 160 and then you say 2 to the power of 160, it becomes an enormous number, right? It's super giant number. So you truncate it to M bits that you want, okay? Then you calculate these peer IDs with this equation that they mentioned. It is not unique. It can be basically not. It can be duplicated some, okay, but it's very rarely that can happen. But even if it happens, it's not a big deal. There are certain solutions for that. Then after that, you map the peers to one of these two to the power of M logical points. So imagine they are the logical points, not they are necessarily your nodes. So you have 2 to the power of M logical nodes. Okay, so you can map any of these. So, I think I'm going to talk about these examples that I have. So we consider M7, like 2 to the power of 7, 128, right? So you have 128 possible logical point that you can assign your nodes. That M, I consider here 7, as they mentioned, based on whatever you want to, whatever number you're thinking of, you can adjust it. So this M is 7, but I have 6 active nodes. So these are the IDs of these 6 active nodes in this ring, right? So let's talk about this with some examples here. So how does Chord partitions data or maps key ID to the node ID? So as they mentioned, you have the key ID, so the key is stored at its successor, okay, or node with next higher ID. So if you have key 5, it will be stored here. If you have key 17, it will be stored here. If you have key 75, 61, 49, they were all stored in the next bigger ID, next higher ID. Okay, so key 81 will be here. Key 16 will be here. 32 will be here. 111 will be here. Okay, 23 will be here. So you have, that's how you store the keys, okay, in different nodes. Then I wanted to talk basically how you can find it, okay? So for example, you have a key 17 in this nodes, right? This is the next higher ID. And how you can find this. So basic lookup, as they mentioned, it can be, okay, I go just next because I have the successor pointers. So I go to the next, I go to the next, I go next till I find the keys, okay? So because this node is looking for key 7, this is the basic things that some people can think of, right? It's a, just go to your next pointer till you find the key. Then you find it, then you can get the information. So this was like algorithm of the basic lookup. But the problem with that is forwarding through that is very slow. Okay, here in my example is of course a really small number of nodes, but in a big network with millions of nodes, that's disaster. Okay, and the complexity is basically ON. So we wanted to basically you want to make the search look like more binary. Okay, so we can get it faster. So this is the whole idea of what they explained. Maybe that was a little bit simpler than what you see here. So this is the idea. So ith entry appears with ID n. This is our ID n. Is the first pair with ID bigger or equal to n plus 2? This is basically should be written this way better. Okay. Mod 2 to the power of n. So basically for I'm going to just talk about this quickly about the finger table as they mentioned already. So basically you calculate the finger table for all these nodes, right? You remember we have M7, we have these 7 points here. So for node 80, you calculate for index I, you calculate the basically next pointer, okay? And so of course for 0 will be 96, the next bigger one, okay? First pair with ID bigger or equal to this. So for this, it becomes this, for this 96. So this, all they are pointing to 96. For this is 5, it will be 112. For 6, it will be 16. I mean, the same equation that they were talking about. Maybe look slightly different, but it's the same exactly. So that will be basically finger table for node 18. All the nodes have this finger table, right? So they have all these pointers. So what about the files? The files also things become same. The same process happens to the files. You have the file names, you do the hashing. Okay, you get this hash, basically the string. Okay, it will become your key. Then you store it. File is stored at the first pair with ID greater than or equal to its key mod 2 to the power of n, because it can be bigger than this, right? It can be bigger than 126, for example, in this. So it should be falling in that. So you generate the hashing, you get the mod 2 to the power of n, you store it in the next bigger ID. So let's say this is the ID. You get this key for 42 for this website or the information in this website. It can be considered like a web caching. It can be MP3 file, movies, whatever you can imagine. This is the key. Okay, that's imaginary key. So key 42 will be stored in 45, right? Next higher ID, right? Anything between 33 to 45 will be stored here. Right? So you have this one stored here. So node 18 wants to look for this key 42, right? Going to look for this website where it's cached, this information. So if you remember, we had this finger table, okay? Now I want to look up for this information, right? So what you do is at node n, sends query for key k, okay? This is the key, to the largest successor for finger entry, smaller or equal to k. If not exists, send query to the successor. So basically, how you can do, you want to send it to the send query, okay, for the key k is 42, to the largest successor, okay, or finger entry is smaller or equal to k. So for 42, it will be this one. The largest, smaller equal to k will be 6, which is basically 16, node 16. So you point to 916, right? You directly go to node 16 based on your finger table. So node 16 now checks its finger table. The same process goes through the same process. It goes to 32, not 45, okay? Because if you check the we don't have time. So if you check the N16 finger table, it will be pointing at this according to this rule, goes here, okay? And all these arrows are basically RPCs, remote procedure calls. It points to 32, and then 32 points to N45, then you get the informations. So in this example, you just have like 1, 2, 3 steps. So this is the lookup with the finger table, the same thing I described just in format of algorithms. You can look it up later. So we already mentioned that this is the complexity, O log n, right? So the question is it fast or slow? Okay, we know it's better than ON, right, the complexity, but is it fast or slow? It's pretty fast actually. For a million nodes, it becomes 20 hops. If you have a million nodes, maximum hop you can jump is like 20. If each hop takes 50 milliseconds, your total lookups will be 1 second, which is fast, right? It's not that slow. I mean, you have a million nodes and your lookup, or you find your information that you're looking for in 1 second. In this case, if each hop has 10% chance of failure, it's a couple of timeout, okay, because you get a failure. So in practice, log n is way better than ON, but still not that amazing, okay. There are some other problems. Failure may cause incorrect lookup, because if you consider this example, if there are fails and if you calculate all the finger tables, you see you get into weird lookup and you cannot find it, okay. It's return like incorrect results or this incorrect lookup. So for this reason, okay, because some nodes can fail, and if you just go with whatever we described so far, you're going to face problem. So you're going to also have a successor list stored, not just one, okay, or just relying on your finger table, but also you want to have your successor to some extent stored, because if someone fails, so you can know what is the next successor. So each node stores a list of its R immediate successor. R can be varies, but usually they do again the log n. Basically, n is the number of the nodes that you have. Okay. So for example, for 1 million nodes, you want to have 20 next node also stored in your successor list because of this problem. Because if they fail, your lookup returns the wrong results. So for example, in this example that we just mentioned, if node 32 fails, okay, your lookup will result in a wrong. I mean, you cannot find the information here. Okay, so that's why it's important to have to store the next like successor. This is a 32. If, for example, I stored 45 also as my next successor, which is just 2 hop away. So even if this fails, still I can find information. This is the same algorithm now modified slightly with considering successor. I mean, it's just same thing that I explained in an algorithmic way. I mean, look it up later. It's nothing special there. So what if the node that has the content fails? Node that is keeping this content fails. Okay, another problem. If that happens, okay, I'm going to look up, I'm looking up, but then the next one here, but this is failed already, so the lookup will fail. So one solution is replicating file or key at R successor and predecessors. Okay, successor and predecessors, not just having it one key. So in this example, if they store the information with key 42 stored in my predecessors, which is node 32, and my basically successor, which is 18, then there wouldn't be any problem even in this case of failure. So that's also happens in a real life. So we already talked about the failure, node failure, the content holder failure. And the algorithm needs to deal with all these dynamic changes. Peers fail, node peers, new node join, leaves, as they mentioned. And in P2P system have a high rate of churn, basically join, leave, and failure. In some cases, as for example in eDonkey, 25% per hour. Okay, it's huge. or in genutilized can be 100% per hour. So 100% of node change from this hour to the next hour. So imagine the dynamicity in the network. So it's a basically common feature in all distributed systems, including wide area, like Planet Lab and clusters like EMU Lab, Cloud like AWS, and so on. So in all the times, we need to update successor and finger tables and copy the keys. Then considering the big number, that can be another overhead to the systems. So they already talk about join. For example, the node joins. Of course, you need to update the key. You need to pass the keys from the basic successor. You need to update the basically reference from your predecessors and so on. We already mentioned all this. Basically, it's the same thing that they will discuss. Get the key that now you have to hold it, okay? Then update the successor, predecessors, links, and so on. So, yeah, that's, I mean, nothing new here. So, yeah, there should be this, I mean, based on all this chore, leaving, joining, failing, you need to have some stabilization algorithms to take care of all these changes. So chart or chord peers periodically runs a stabilization algorithm that checks and updates pointers and keys, okay, because nodes fail, node joins. So they are periodically checking these changes, new changes. So to ensure non-loopiness of fingers, eventual success of lookup and this complexity, lookup with this complexity, we need to basically run the stabilization algorithm often. And another thing is strong stability takes this like awful complexity, okay? Imagine n is number of nodes. So this is very bad complexity or very high complexity. So if you want to have a strong stability, or you make sure there is no failure in the system, then or all the pointers are correct all the times, and all that, taking care of all those details, you need to go through all this complexity. So I talked about this chart. It's like the dynamicity, like 25 to 100% of the total number of nodes in the system can change, join, leave, fail. And so this leads to excessive or unnecessary key copying. Remember that the keys are replicated, right? So it's not as you mentioned, like you replicating keys, like in like 20 successor predecessors, you're replicating, you holding the pointers for the successors. So imagine all that, okay? So the stabilization algorithm may need to consume more bandwidth to keep up with all these changes, because one leaves, the next one joins. Now you have to update all these references, all the keys, replicate them again, replicate the new join, new node to other nodes. So main issue is here is that files are replicated too, okay? While it might be sufficient to replicate only meta information about the files. So we don't always necessarily need to replicate the files. Sometimes it's just enough to replicate the metadata of the files in order not to consume a lot of bandwidth in the network. Another idea is virtual nodes. So hash can get non-uniform or bad load balancing. For example, you have this node, then another node is here. So all these keys here going to store in this particular node. So in order to solve this load balancing issues, you can use virtual nodes. What is virtual node is treating each node as multiple virtual nodes behaving independently. What it means, if you have that circle, let me go back. Oh, where is it? To the example, let's say here, okay. If you have all this, then you treat all this node as a set of virtual nodes. For example, you say, okay, node 80 is, this is the physical node you have. You may consider this as a 3 virtual nodes with this ID, and this ID, okay? Or this ID, this ID, this ID. Because it's at the end, they are logical points, right? It doesn't matter. They are totally logical. So node 80 can be 80, okay, ID 80, ID 2, right? Then store ID 100. It's a virtual node, right? There are logical points, so I can assign any logical point I want to this. I hope I confused you enough. Okay, so I go. Is it clear what I'm saying? They are at the end, they are logical point. Okay, I'm assigning. I say this is node. I'm assigning to this basically node 80, but I can assign it more logical point in order to do the load balancing. Because if you have a, where should I don't have white paper, whatever. If you have like a circle here, so it comes about the circle, like hashing circle, then if you have one node here, then the next node is all the way here. All these keys going to store in this particular node. So you're not going to have a nice load balancing. What else? So let's talk about the concluding thought. So why don't all services use P2P? I mean, today we are all talking about P2P is great, P2P is awesome, safe, okay, secure, scalable, and so on. But there are certain issues. There are high latency and limited bandwidths between peers, between two peers, not considering the whole network, okay? Between two peers, there's a high latency and limited bandwidths, comparing that to the servers in data centers. Of course, there are a giant bandwidth between two servers and very, very low latency when we're talking about two servers. The user computers are less reliable than managed servers. The user computers, of course, fails more often than the managed servers. And there is another one is the lack of trust. I mean, Dorley is happy now. We are addressing that. Okay. So the lack of trust is another issue in P2P systems because peers cannot easily trust each other, and securing distributed hash table routing is really hard. And I mean, when we had this slide or we come up with this slide, at that point it was unsolved in practice. It's really, really hard to secure distributed hash table routing. It's not a trivial problem. It's a hard task. So that's why not all the systems are using P2P. P2P is great for certain applications, but not always for all the applications. It's not like a silver bullet for all the problems we have. So distributed hash table seems promising for finding data in large P2P systems, right? You see, even you have millions of nodes, it's quite fast, as they mentioned. You see like in like 300, 400 milliseconds, you can find your information. Decentralization seems good for load and fault tolerance, but the security problem is difficult. Churn is a problem, particularly if login is big. If the login is big, then all those join, leave, failures becomes a big issue because it's not like a node system is failing once per week. It's like 100% of the nodes are changed from this hour to the next hour. So it's a lot of dynamicity there. And to handle all those, it can be, if this would be a big number, log n, then that can be an issue. So distributed hash tables have not had the impact that many hoped for, that it's going to solve all our basically distributed system problems. But of course, it's helping a lot in a lot of systems. So what distributed hash tables got right? Consistent hashing. So it's an elegant way to divide a workload across machines. So if you get the idea, you can see how beautiful is that, considering you have all these machines and you want to divide the workload. So imagine, just think about it, all the information that is available in BitTorrent, the amount of data. Okay, it's huge, right? It's huge, really, the amount of data that's available. But you're using it, I'm using it. I don't feel I'm losing my space. My hard disk is full now. But imagine how nicely we could divide this workload across all these machines. So it's very useful in clusters. It's used in Amazon Dynamo and other systems. And replication for high availability, efficient recovery after node failure. We already talked about you replicate the information, or you replicate at least the metadata of the files in different nodes, not just one node. And you know that. I mean, when you go to you want to download a certain file, you see all these peers that providing the download, all these leaders that sucking information. So you see how much basically how many replication is happening there. Incremental scalability and other things that the distributed hash tables got right, because it's as simple as adding new nodes. You can increase the capacity. You can improve, basically increase the capacity. And the self-management is like, which is configuration doesn't require, basically, it's not difficult. It doesn't require as much time. It's minimal configuration systems. So virtual links and consistent hashing used in Cassandra, React, Baltimore, DynamoDB, and other key value stored systems. And this is the current status of Chord project. Okay, it's a file system is CFS or IV built on top of Chord. DNS lookup service built on top of Chord. Imagine. Okay, that's amazing. So Spawn research on many interesting issues about P2P systems. After basically this paper coming up with this idea, a lot of interesting system came up, a lot of interesting research happened about P2P systems. And you can even take a look at the project itself and see what are the latest developments. That's it. I tried to be as fast as I could. Is there any questions I can take? It's really clear, you got it? Or are you just too tired to ask questions? Okay, I'm sharing this. If there is no further questions, we'll be done with today's class. No?
We can ask we can ask questions when also about certain topics when we get the individual meeting, right? Just quick questions like that. It won't.
Yeah, you can. Oh, before you leave. Yeah, you of course you can ask. I mean, there is no issue. You can even drop me an email. I try to be as quick as I can to return to you with the answer, or you can talk to me. But yeah, I mean, yeah, of course you can. I mean, when you have a meeting, you can ask me anything. There's no issue with that. But another things about the project, there's something that no one utilized for the project one. We have discussions in Canvas, okay? So if you go to the Canvas in discussion under the data assignment, you can see that you have project one discussion, no one used it. Project two discussion. So if you have question about project two, why don't you ask other students? And you get grades about it. This was the same rules for the project one. I mean, no one used it, and maybe you're not interested, it's fine. But if you are wishing to, you can use basically discussion prompts. Last time it was really nice questions, a lot nice discussion happening in the pro. Because I mean, you are doing at the same time the project, so you have questions. Maybe some other students can answer, and another student comes and correct you both, and becomes like a nice source of information. For
I think-
question, you get of course point. For right answer, you get more points.
Yeah, I think what happened is that we didn't use the right platform because we kind of collaborate over Slack.
Yeah.
So I think
Maybe
we
you can send me a screenshot of a Slack.
we can move maybe to this platform.
Yeah, the idea here is for all of you, not just you collaborate with your own team, but your team collaborate with other teams. It's like collaboration. And I will, yeah, no, I have it already, project 2, so project 3 also. So yeah, that's it. I just wanted to mention this. I mean, if there is a questions about the project, it's way better to ask it here. If you didn't get the answer, if everyone had the same question, of course, I'm available for answering.
Okay.
Okay.
Yep.
Okay, guys, have a nice night. Enjoy the rest of not much left, but enjoy it. See you next week. For the next week, we have a presentation by group 5. Okay, so we shift all the presentations to 1 week down.
Yeah.
Okay, see you guys.
We need to wait, Mari?
Oh no, you wait. If you have all the members here, your group waits so we can finish that project 1 discussion. Okay.
Thank you, Mari.
Okay, see you guys. See you next week.
See you. Bye.
Thank you guys. Take care.
Evening. Bye.
See you. Bye. Bye. See you.
Okay, so I'm just opening up all the files that we modified.
Maybe I can talk about the first one.
Okay, go ahead.
Okay, so Q1, as you remember that those are the two first problems. The one is to find the top word, and the second one is to use channels for adding some different numbers. For the first one, basically it's a little bit different than the other ones because we were using regex, and also we were validating in that part we have it was a little bit complicated. We were validating the word that we were doing was actually a word, right? Because you wanted to validate that we were according to the I don't remember what is the function that you wanted to we needed to use.
Yeah, I think what he means is that for this specific problem, we just needed to use a regex expression, right? So, and then later on in the assignment 1.2, we had to use the run, like the Unicode instead of
Unicode, yeah,
regex.
that other one. Okay. So that was the first one, and the second one, the one that is related to the Q2, we did it a little bit different. In this part, we are first. Can you please go down a little? Yeah, there. We are separating the data, so we are trying to each channel has the same amount of data. So at the end, as you can see, I am doing some cuts. So I'm putting the data into the number of channels that we are going to generate. So and then we are getting the result that you wanted.
Mm-hmm.
Okay.
Okay.
So
okay.
Okay, maybe I can explain the second part of the project. Can I share it or?
Yeah, sure.
Yeah, I mean, it may be easier. You can see my screen, right?
Yes.
Yeah.
Okay, so for this part, we had to implement the MapReduce in a sequential way. So here in the map, we are creating the intermediate files and reduce intermediate files. So we create each file and we put it in an array of files. And then we use the iHash function to determine on which file we should put each word. And then we put each word in a JSON format. So we will have the word, and we hard code a one in the mapf. So we will have words repeated in a JSON format. And then in the do reduce, we read each file. And sorry, I forgot to mention that here in the mapf, we are using this function to determine if, I mean, first we use the fields to split the words on each file, and then we use this function to determine if it's a word. And if it's a word, we append the slice. Then on the do reduce, we read each file, and basically we append into the array each one. So we will have an array with all the occurrences, and this way in the reduce f, we just have to check for the length of the array that have all the ones. And yeah, I think that's it for this second part.
So I don't know if you want us to run the test cases.
Yeah, please. It's just saying, just curious to see.
Can I? I have already this set up, Charlie. Can I show?
Oh, okay. Yeah, sure.
Okay, so well, I just okay. Let me go. Oh, sorry. Go to the just assignment one. I think this is direct, right? Yeah. Okay. So for this, I have to run. Oh no, this is for the tree. Yeah. This is kind of short. Okay, let me do that. You can see my screen, right? Because
yes.
Okay. Okay, so that's the second, and then the CH. It's taking a while. There it is. And then, well, this is for the second part. I don't know, do you want to add anything else, Charlie or Pedro, to the second part? So
No, not really.
Okay.
No, I think that's it. Just that in the end we will have a JSON with the word and the number of occurrences.
Okay. Okay, for the third part, we had to modify a little bit the mapf and reducef functions in order to to accomplish the inverted index problem, right? So instead of counting words, we just detected the file names of the books or text where a file appears, right?
Luis, you need to open the WE.
Sorry?
You need to open the other file, the WE.
Oh, okay. This is the one.
Yeah,
right?
that one.
Oh, okay. Not this. Okay. Thank you. Okay. So, yeah, we modified those functions in order to now solve a different problem instead of counting words. Yeah, just check the number of text where a certain word appears. And also in the schedule, what we did is like based on the number of workers, we started to populate a channel with the work instead of with the work. For example, we populated this channel available work, and then based on the number of workers available, we have like a concurrent function, one that is checking for workers to be subscribed to the MapReduce algorithm, and then once a worker is registered, then the scheduler assigns the next available work to that worker, right? So we also added some logic here. For example, if we don't get an okay that the worker completed the work successfully, then we are sending those arguments that the worker had, a failure that the worker that failed had. So the available work had that that work that was not processed correctly. So once a worker is available to work on this, then it will be processed. So yeah, that was the approach that we followed. And then once all the workers have done, then we are just calling the done, just to tell here the schedule that all the workers have completed their part. So yeah, that's it. And this no. And I think that's it. I don't know if you have anything to add.
Nope.
Okay, good.
I think that's pretty much.
That's fine. How did you find it? Was it hard?
I think Well, personally,
I think that.
Go ahead.
Yeah, go ahead.
Okay, well, it was fun actually. Probably the complicated part was to understand like the whole project, which are the files that do something, and we have to consume those methods or those functions, and where to call them. And yeah, I mean, it was fun actually, more fun than.
Yeah, I think the hardest part was trying to find out what do you want. What do you want us to do? Because yeah, you said you were describing what we're expecting in the functions, but well, there could be a lot of things that maybe you were thinking that we were going to do. The reality is that, well, just reading is not like the same like talking or and asking questions about everything, because at the time when you are doing that, you have a lot of questions and there is no one that can actually answer. So we were assuming sometimes some things, and they were like, well, maybe this approach, but I don't know. Well, we will try. So I think that was the hardest part from my side.
So it wasn't as complicated as you were thinking, or as you were afraid of.
No, but we had to spend some time also to learn the Go language, because none of us had used it before.
Yeah, I understand. Yeah. Anyway, it's like you never heard about it before? Just curious.
Sorry, can you?
You never heard about Go language?
No.
Yeah.
I didn't.
No.
Okay. I hope you. I mean, it's not just about this course. It will be useful at some point for something. Okay. It's who knows? Okay. Anyways, developed by Google. So
well,
hopefully.
Yeah. The fun thing about Go is that you can do a lot of things in an easy way. But the other thing about Go is well, it doesn't work like normally you are used to work with another programs or another languages.
I agree. True. Anyway, we did it. Nice job. Thank you guys. So it's you are finally, how to say, you keep up with the rest of the groups now. So that's great.
Nice.
Yeah.
Okay, guys. Take care. I mean, if you have a question, like a doubt like this for the next project, I mean, use the discussion forum, and I'm pretty sure there would be someone answering. If you see no, you cannot get the answer, then I'll be here to help. Anyway, at the end, it's not about evaluating your programming or how to say teaching your new language, or you know, it's nothing at all about that. It's about getting the concept. Just that's it purely. So
okay.
Okay, guys, take care. Then have a good night. See you next week.
Thank you.
Thank you.
See you guys. Take care.
Yeah.
Bye. Bye.
You too. Bye.